Good afternoon. We had looked at induction motor torque expression in the last class. In fact, we started from the equivalent circuit of the three-phase induction motor, saying that on a per phase basis, the stator winding is going to have a resistance R1, a leakage reactance X1, which is actually indicating the flux, which is only linking with the stator winding, not with the rotor winding at all. And if we assume that we are applying a voltage V1 for the stator winding, after the drop that is taking place in R1 and X1, what is left over, that is actually the stator induced EMF, because the self inductance will induce an EMF in the stator winding itself. The revolving magnetic field that is created by the stator current will be visualized by the stator winding also as a varying flux. And we are going to have on the rotor side, whatever is the induced EMF, that is going to be E2, and this is going to be R2, and this is going to be X2, which are the stator winding leakage reactance and resistance respectively, and the rotor winding is short circuit. So R2 and X2 are rotor winding resistance per phase and rotor winding leakage reactance per phase. Now we said that once the rotor starts rotating, the induced EMF in the rotor is going to be proportional to slip. So initially the slip is 1. Later on the slip is going to decline. Because the slip is declining, this voltage will also eventually become SE2 and the frequency will also come down. So rotor induced EMF frequency, that is also proportional to slip S. So we are going to have the reactance becoming now S times X2. So we wrote I2 equal to S times E2 divided by R2 plus JSX2, and we divided the numerator and denominator by S, that is the slip. So this becomes E2 divided by R2 by S plus JX2. And once we made this E2 also at 50 Hertz, and V1 is going to be, or else E1 also is going to be at 50 Hertz. So we can combine these two, and that is where we drew the overall equivalent circuit somewhat like this. This is R1, this is X1, which is the leakage reactance and resistance of the stator winding. This is the per phase voltage that we apply. And we are going to transfer this R2 dash by S. That is R2 by S we are transferring to the stator side, which is R2 dash by S. And we are going to have X2 dash here. And this is short circuited. And the current that is flowing here, we call that as either I2 dash or I1. That is going to be the current. So we should be able to write this particular current as I2 dash is going to be V1 divided by R1 plus R2 dash divided by S plus JX1 plus X2 dash. I can write it that way, or I can write real part square plus imaginary part square root of that. This is going to be the current. And we said this current is going to be enormously high when we look at a slip value equal to 1. That is during starting condition, because R1 is very small, R2 dash is also going to be very small. And leakage in an induction motor is also not going to be big, because it is all ferromagnetic material with which we are making the core of the stator as well as core of the rotor. So the leakage will be very minimal. That is the reason why we said starting current is going to be almost 5 to 8 times I full load or I rated. Compared to the rated current, this is going to be really, really large. And we also said if we are saying that R2 dash by S is the resistance which is taking in all the power that is entering through the air gap into the rotor. So I can say rotor input power per phase. That is going to be I2 square R2 divided by S, or if I refer to the whole thing on the stator side, it is going to be I2 dash square R2 dash by S, but power dissipated in the rotor resistance, that is going to be I2 dash square R2 dash. So mechanical power output, if I try to look at it from the rotor side, that is going to be equal to I2 dash square. So this is again all per phase. What we are writing is all per phase. So per phase mechanical power is going to be I2 dash square R2 divided by S minus I2 dash square R2 dash. So that will come out to be I2 dash square R2 dash multiplied by 1 minus S divided by S. So from this we actually said that the three-phase mechanical power, which is going to be 3 I2 dash square R2 dash multiplied by 1 minus S divided by S. So that is going to be written as, let us say, 3 I2 dash square R2 dash multiplied by 1 minus S divided by S. And if I am talking about mainly torque, I should be able to say the three-phase mechanical power itself is TE multiplied by omega R. So I can write TE is going to be this divided by omega R. So this is how we got the electromagnetic torque expression. And we said because omega S minus omega R divided by omega S is defined as slip S. So I should be able to write from here this as omega S multiplied by 1 minus S will be equal to omega R, which is the rotor velocity. So I can write TE is equal to 3 I2 dash square R2 dash, and I can substitute for omega R as 1 minus S times omega S, and this 1 minus S and 1 minus S will get cancelled. So that is how we got the expression, and I substituted for I2 dash with this particular expression. So I can write this as 3 V1 square R2 dash divided by S omega S divided by R1 plus R2 dash divided by S the whole square plus X1 plus X2 dash the whole square. And from that we drew the speed torque characteristics for two regions of operation where slip is close to 0 and slip is close to 1. And I can say this is how the characteristics were looking. So if I just say this is going to be the speed axis, so omega R is increasing in this direction, whereas slip is increasing in this direction. And let's say this corresponds to omega S and this corresponds to 0. So I'm going to have the linear region somewhat like this and the hyperbolic region somewhat like this. And this happens to be the TBD point. So this is actually Breakdown torque, this is starting torque. What I have got here is the starting torque. Whereas when I am looking at this as the total torque, that is TBD, breakdown torque or maximum torque. And this is going to be S max T, slip at maximum torque. Last time I told you that if the torque expression what we have got here, if I try to differentiate dTe divided by ds equal to 0, that gives what is the slip at maximum torque. So I can say this particular slip at maximum torque is going to be approximately R2 dash divided by R1 square plus X1 plus X2 dash the whole square root. Or approximately I can write this as R2 dash divided by X1 plus X2 dash. And when I am looking at what is the TBD or Tmax, maximum torque, that will be approximately 3V1 square divided by 2 omega s multiplied by X1 plus X2 dash. And if we are looking at a normal induction motor where the slip is going to be anywhere between 0.01 to about 0.04 or something like that, very, very small drop in speed will be observed until full load torque. This is going to be full load torque. Nothing more than this. And this is one reason why the induction motor is not a great candidate for electric vehicles because the starting torque itself is not much higher than full load torque. If I try to look at the ratio of starting torque to full load torque, it will be only about 1.5 at the most. So we will have anywhere between 1 to 1.5. That is what is going to be the typical figure for a three-phase induction motor. And if I look at what is TBD divided by T full load, that will be anywhere between 2 to 3. So the maximum torque capability of the induction motor is also pretty much limited. So we are not going to have a very high torque capability or overload capability for the induction motor. So, and starting condition is like generally it is going to have a very, very large current being drawn, but the starting torque would not commensurate with whatever is the amount of current drawn. So, which is definitely not good for the motor itself, especially in an electric vehicle kind of situation where it has to haul a very, very large torque in the beginning. The entire weight of the vehicle has to be hauled, and the friction against the road, like for the wheels against the road, that has to be overcome, and slowly the wheels should start rolling, and that will require a huge amount of torque. And that is one reason why in many of the electric vehicles, if you look at the average power or average torque requirement, that will be much lower as compared to what is required during starting. So the motor rating would be much higher than what is the average required rating as far as the power delivered by the electric vehicle is concerned. On an average basis, the power requirement is low, but for initial starting, the overall torque requirement becomes extremely high. Okay. So one more thing we said was, if I try to look at the starting torque, we will have the same expression, which is actually 3V1 square. You look at this expression, what we wrote, 3V1 square R2 dash divided by S omega S. So I can again say R2 dash, S is 1 during starting, and I have to write omega S, and this is going to be R1 plus R2 dash the whole square plus X1 plus X2 dash the whole square. Slip is 1. So I can also write this as 3 I2 starting whole square multiplied by R2 dash divided by omega s. So even if I'm going to have I2 starting to be a very large value, during running condition, what we normally see is I2 full load the whole square R2 dash divided by S full load multiplied by omega S. So this S full load, whatever we are looking at, that is only about 0.01 to 0.04. That is the reason why when you have such a small number in the denominator, that actually makes this factor get multiplied by 25 or 50 or something like that. So the overall torque, what I see during full load becomes quite high as compared to what I see during starting. So if I try to take the ratio of T starting divided by T full load, this is going to be I2 starting divided by I2 full load whole square multiplied by S full load. So if S full load, whatever we are looking at, if it happens to be higher by chance, then my machine might give a very good starting torque, good amount of starting torque. But if S full load is smaller, then I will have very small starting torque even for a large starting current. But on the other hand, if I'm going to have S full load to be large, we already wrote this. We said if I have mechanical power output to be 1 minus S times 3I2 square R2 divided by S, whereas the rotor input power is going to be 3I2 square R2 divided by S. So this is going to be our rotor input power. So this is rotor output. Mechanical power is also incidentally rotor output. So I can say rotor efficiency is going to be rotor output divided by rotor input, which is 1 minus S. So if by chance S full load is large, rotor efficiency is going to fall. So if the slip is, if SFL is large, motor will be inefficient under full load condition. So I would say if SFL is large, motor will be inefficient during running condition, but the starting torque will be somewhat larger. So there will be contradictory requirements for keeping the motor efficient and keeping the starting performance fairly satisfactory. So we cannot have good running performance and good starting performance simultaneously. Both would not be possible in a normal three-phase induction motor. We are not going to be able to get both good running and good starting performance simultaneously. If one condition is satisfied, the other condition may not be really possible. We can only kind of hit at a trade-off between having fairly okay running performance and fairly okay starting performance. We will not be able to get both of them to be exceptionally good. That is the bottom line. Okay. So let us quickly look at one numerical example on a three-phase induction motor. So let me try to work out one numerical example. So the problem statement is somewhat like this. A 440 volts 50 hertz, 6-pole, Y connected induction motor has R1 equal to R2 dash equal to 0.3 ohm. X1 equal to X2 dash equal to 1 ohm. Full load slip is equal to 0.05. Calculate motor current, torque, efficiency, and speed at full load condition or rated condition. That is the first thing that is being asked. Then the second thing that is being asked is maximum torque, and the third thing that is being asked is slip at which maximum torque occurs. Fourth one that is being asked is starting current. And the fifth one that is being asked is starting torque. First of all, you have to realize that it is a star connected induction motor. If it is star connected induction motor, first thing you have to remember is I phase and I line are equal to each other. Whereas V phase is going to be V line divided by root 3. And what is given generally in any induction motor problem or any three-phase problem is this 440 volts will be VRMS line. So whatever is given clearly, that is going to be VRMS line voltage. And if at all some current is given, again I should say the current given will be IRMS line current. Unless it is specifically specified that it is phase current or it is peak current, you have to assume whatever is given, that is RMS line current. And similarly, if some power rating is given, let us say some 7 kilowatt or 10 kilowatt, something is given, what is specified will be generally output power rating. So it goes without saying that in any electrical machine, the power rating given is output power rating. The voltage rating given is always RMS line voltage rating. And similarly, the current rating that is given, that is whatever is written on the machine, nameplate details of the machine, all of them will always correspond to three-phase power output, and whatever is the speed that is specified is what is the full load speed when you are loading the shaft to the fullest extent, what is the kind of speed the motor is going to manifest, that is the full load speed that will be written on the nameplate details. The voltage and current that are written are again RMS line values. Okay. Having said that, now we will go ahead and try to work out the solution for this problem. First thing you have to remember is if it is 6-pole and it is 50 hertz, if I want the speed in radians per second, that is the synchronous speed, if I want to calculate in radians per second, it will be 2 pi f divided by P by 2. So this is going to be 2 pi multiplied by 50 divided by 6-pole machine, so this will be 3. So if I calculate this, it will be roughly 6.28 multiplied by 50 divided by 3. So this happens to be 104.67 radians per second. If you want to calculate in RPM, it will be 120 F by P. So for 2-pole machine, it will be 3000 RPM. For 4-pole machine, it will be 1500. For 6-pole machine, it will be 1000 RPM. Okay. Now what is being asked is current, torque, efficiency and speed at full load condition. So let us try to calculate first of all speed. So speed is going to be 1 minus s times omega s, and s is given to be 0.05. So you can say it is 0.95 times omega s. If I am talking about in radians per second for omega s, I should substitute this. Otherwise, I should substitute this as RPM. So it can be 950 RPM or correspondingly whatever is the radians per second. It's not a big deal. Now we can calculate what is motor current. So motor current, first of all, I can calculate. So motor current, if I try to calculate, I should use the expression what I wrote, if you may recall in the previous slide. So we said that this this happens to be what is the motor current. What we have got here is the motor current. So let me try to calculate that. So that is going to be V1 divided by R1 plus R2 dash divided by S, the whole square, plus X1 plus X2 dash the whole square root of this. That is what is the motor current. And please remember, it is a star connected machine, so it is going to be phase voltage is going to be V line by root 3, and V line happens to be 440 volts. So I can write this as 440 divided by root 3. That is what is the phase voltage. And R1 is given to be 0.3. So I should say 0.3 plus 0.3 divided by 0.05, the whole square, plus leakage reactance is given to be 1 ohm each. So this is 2 square, and I have to take square root of this. Okay. So this will come out to be, let me first of all write 440 divided by root 3. That happens to be 254 volts. So I'm going to write this as, this is equal to 254 divided by, so this is 0.3 divided by 0.05, and that is coming out to be 6. And that has to be added to 0.3. So this is going to be 6.3 square plus 4. And I have to take the square root of that. So that is 6.61. So what I am getting here is 254 divided by 6.61. So this comes out to be so let me multiply this by 254 divided by 6.61 happens to be 38.43 amperes. So I'm going to get this as 38.43 ampere. Now I can calculate the torque. So torque will be 3 this is I2 dash or I1. Either way is fine. So I2 dash square R2 dash divided by S omega S. That is going to be the torque. So I can calculate this as 3 multiplied by 38.43 square multiplied by R2. R2 happens to be 0.3 divided by slip at full load is 0.05, and we had calculated synchronous speed as 104.67. Okay, so if we calculate this, let me just do this. It comes out to be 253.94. So what I'm getting as the torque is 253.94 Newton meter. So I have got the current already calculated. I have got the speed already calculated. Now I have got the torque also calculated clearly. If I want power in this particular case, what I need to do is 253.94 multiplied by omega r. And omega r is 1 minus s times omega s. So I can simply write this as 253.94 multiplied by 104.67 multiplied by 0.95. This is the watts power output of the induction machine. Okay. So efficiency is the next one that is being asked. So to calculate the efficiency, we should calculate this as output power divided by input power. And input power will be root 3 VL IL cos phi. And output power is whatever we calculated here. That is 253.94 multiplied by 104.67 multiplied by 0.95. So that is about 25.25 kilowatt. So this comes out to be 25.25 kilowatts. So here we don't have cos phi. Normally cos phi you can calculate as cos of the angle, which is actually x1 plus x2 dash divided by r1 plus r2 dash divided by s. So this will give us what is phi, and cos of that will be the power factor under this condition. Let me try to calculate this. This is 0.3 divided by 0.05, which happens to be 6. So this is tan inverse of 2 divided by 6.3. Is it 2? Yeah, it is 1 ohm. That's what I think we got. What we got was 1 ohm. Let me try to look at this. The parameters of the, yeah, this is 1 ohm. So 1 plus 1, 2. That is what is this. So this comes out to be 17.61 degrees. So cos of 17.61 will be about 0.95. But generally you will not have such a high power factor. We have made some approximation. That is the only reason why it is coming out to be 0.95 or something, which is way too high. No induction motor will have such a good power factor. So if I try to calculate for this particular condition, it is going to be 25.25 divided by root 3 divided by 440 volts, and the current happens to be 38.43 amperes RMS, and the power factor is 0.95, and this comes out to be something like 90.75%, which is really a very, very high efficiency. So this happens to be 90.75% efficiency, which is kind of unrealistic. Doesn't matter. So this is how you calculate the efficiency. Now, what is being asked is slip at maximum torque. So let me try to calculate that. So slip at maximum torque, we wrote that as R2 dash divided by R1 square plus X1 plus X2 dash the whole square root. So this happens to be R2 dash is 0.3 and R1 square is 0.09 and X1 plus X2 dash the whole square is 1 plus 1, that is 2 square, which is 4, and square root of this. So this comes out to be 0.3 divided by square root of 4.09. So that is 0.1483. So this comes out to be 0.1483. This is the slip at maximum torque. And the third thing that is being asked, so if I may call this as 2, the third thing that is being asked is TBD itself, that is the maximum torque itself. So that is essentially going to be R2, no, this is actually 3V1 square. We wrote that expression also. So we wrote the maximum torque expression happens to be 3V1 square divided by omega s divided by x1 plus x2. So this is 3V1 square divided by 2 omega s multiplied by x1 plus x2 dash. So that is 3 multiplied by 440 divided by root 3. Please remember, always you have to substitute per phase voltage. So that is 440 divided by root 3. Here what we are substituting is line voltage and line current. So you don't have to worry. Whereas here it has to be 440 divided by root 3 the whole square. And omega s is always in radians per second. So 104.67 and x1 plus x2 dash happens to be 1 plus 1, which is 2. Okay. So this root 3 square and this 3 will get cancelled. I can directly write 440 square divided by 4 multiplied by 104.67 coming in the denominator. So I can write this as 440 square divided by 4 divided by 104.67. So that comes out to be 462.4 Newton meter. So you can very well see that TBD divided by T full load is not even 2 in this particular case. 462.4 divided by 253.94. So it's not even 2. So it is less than 2. So the breakdown torque is not as high in this particular case. The next one is starting current, then the starting torque. So let us try to calculate the starting current. So I starting is going to be V1 divided by root of R1 plus R2 dash the whole square plus X1 plus X2 dash the whole square. V1 happens to be 440 divided by root 3 and R1 plus R2 the whole square is 0.6 square and this is going to be 2 square. So it is 4.36 square root. So this is going to be 440 divided by square root of 3 and 4.36. So this is 121 ampere. So what we are getting as the current is 121.66 ampere. Whereas the full load current what we calculated was only 38.43. So if I divide this by 38.43, so we are having only about 3 times the normal current. So that is also generally not, so common. So here what we are getting is I starting divided by I full load happens to be 3.166. Normally what we expect this to be is anywhere between 5 to 8 times. But if a particular induction motor has a larger resistance and larger leakage reactance, the leakage reactance will be larger and larger if I'm having a larger and larger air gap between stator and rotor. If I say this is the stator, the rotor will be a concentric circle. But if the gap is very high, air gap is very high, because the reluctance of the air gap is large, the current drawn will also be large and the leakage will be pretty large. So when you design the induction motor, if you want the starting current to be small, then you can have larger leakage, but that will also result in poorer efficiency. So this also again emphasizes that the good running performance and good starting performance both cannot be achieved simultaneously. They are generally contradictory requirements. That's what you see normally in a three-phase induction motor. One more thing that is being asked is starting torque. So let us try to calculate the starting torque. So this is starting current. So starting torque is going to be 3 I2 square R2 divided by, or I2 dash square R2 dash divided by S omega S. S is going to be 1 because it is starting condition. And I2 happens to be whatever is the starting current. So I should say 3 multiplied by 121.66 square multiplied by 0.3 divided by 104.67 radians per second. This happens to be our, the starting torque that you might expect this induction motor to generate. So this value comes out to be 127.26. So this is only 127.26 Newton meter. Whereas we saw that the normal torque is 253. So look at this. We are getting even almost half of whatever is the full load torque, because our resistance and leakage reactances are probably large, due to which starting current was limited. Because starting current was limited, the starting torque is also limited. So in general, induction motor, three-phase induction motor, although it is really maintenance free, it is rugged, it is definitely capable of running quite well without any maintenance. One major problem we see with three-phase induction motor is its starting performance is very poor. To haul the entire electric vehicle from rest condition, you will require a very, very huge torque, for which you will require a large current also. And whether the battery will be capable of supplying such a thing, that is a very big question. So, in general, induction motors, especially because they are excited only from the stator side, there is no magnetism available on the rotor side. The kind of power factor you see, the kind of reactive power requirement you see in those induction motors are very high. So in general, if I try to write the disadvantages of conventional three-phase induction motor, particularly with respect to electric vehicle application. Starting current is large, whereas starting torque is not as high. Second thing is rotor has no source of magnetism. So reactive power requirement, that is magnetizing requirement from the stator is very high. So power factor is lagging, and at the most you will have only about 0.8 or 0.85 as the power factor. Nothing better than that. And inverter is the only way you can control the speed. And because it is drawing a huge amount of reactive power, efficiency is not that high. And there will be limitations on the air gap, how much you can have as the air gap between stator and rotor. Because if the air gap is increased, just because there may be some kind of vibration, torsional motion, the rotor can go and hit the stator. And you don't want that to happen. It is deadly. If in a big induction motor, if the rotor is hitting the stator for some reason. So generally we may have air gap to be a little large, but if air gap is increased, then reactive power requirement will increase. And that means we are going to have lower efficiency. So we are really not looking at induction motor. If efficiency wise, it cannot really match with permanent magnet synchronous motor. Two aspects we need to see on the induction motor side. One is braking, and the other one is speed control. So we need to look at these two aspects if we want to use this in an electric vehicle. Because if we are really looking at the vehicle being stopped abruptly, maybe to avert an accident, maybe to make sure that, at red light, you are able to stop very clearly. Then braking or controlled stopping. So braking is basically controlled stopping of an induction motor. So this is going to be controlled stopping of an induction motor. So if I really want to stop the induction motor in a controlled manner, typically in electric vehicles, what we use is regenerative braking. So what we mean by regenerative braking is, if I am going to have, let us say normally in induction motor, we said that if this is the stator revolving magnetic field which is rotating at omega s, and let's say this is my rotor, the rotor will rotate at a speed which is less than this omega s. Let me call this speed as omega r. So normally we are going to see omega r less than omega s. But if I want generator operation, the first and foremost condition has to be omega r should be greater than omega s. That means if I am looking at omega s minus omega r divided omega s, which is actually slip, slip will be negative for generator. But slip is going to be positive for motor. So when you are looking at slip being negative, if I am trying to look at 3I2 square R2 divided by S omega S to be the torque value, because S is negative, the torque happens to be negative, so the power will also be negative. That means instead of the motor drawing the power, it will be able to supply back the power if it is connected to the three-phase grid, or if it is connected to a battery through the inverter, it should be able to feed back the power. That is what you would see normally. When can omega R become greater than omega S? So that can happen if vehicle is moving downhill. If by chance a vehicle is moving downhill, you can have omega R greater than omega S. If you may recall, we drew the induction motor characteristic somewhat like this, and we called this speed as omega S. So if I'm going to have omega R greater than omega S, obviously the operating point is going to be somewhere here. So if I say this is the torque axis and this is the speed axis, you can very well see that the torque is negative whenever I am talking about a speed greater than synchronous speed. So when the vehicle is moving downhill, we can have negative torque developed, so which is actually corresponding to generator operation. So if we are looking at normally in motoring operation, if I say that 0.05 happens to be the slip, it was given full load slip is 0.05 in the previous problem what we worked out. So under such a condition, if we are asked to calculate what is the rotor frequency or induced EMF frequency under full load condition. So F2 is generally specified as S times F1. So if I am talking about S as 0.05 and stator side frequency is 50, this happens to be 2.5 Hertz. So what we are getting as the frequency is really, really small, and it is still a positive frequency. Whereas if I try to look at regenerative braking operation, under such a condition, we are going to have negative slip. So if I am looking at rotor frequency, it is going to have minus S times F1. So it looks as though it is a negative frequency. You have to think about it, what you mean by negative frequency. Obviously, frequency means so many oscillations per second. You can't have minus of so many oscillations per second. So please think about it, what it means to be negative frequency. In the case of an electric vehicle, we are generally going to have this as the battery, and between the battery and the inverter, there will be a DC to DC converter, because the battery voltage may not be exactly matching with inverter requirement. So what I have as the battery voltage is a fixed voltage. Maybe it is a 220 volts battery. So I'm going to have only 220 volts across this. Now what my inverter requires may be 500 volts, in which case this DC to DC converter has to work as a boost converter. Now the output of this is given to DC to AC voltage source inverter or three-phase inverter. So now this is going to deliver, so this is VSI, DC to AC three-phase VSI. Let me write this as three-phase VSI. Now, what is coming out of this? That will be a three-phase output, which will actually go to the induction motor, and induction motor is coupled to the load, which is the EV. It is coupled to the EV. Now, when I am having, let us say, the vehicle working at 1450 RPM, and I am feeding this induction motor with 50 Hertz supply. Maybe it is a 4-pole induction motor. Okay. So for 1500 minus 1450 divided by 1500, that happens to be the slip, what I can calculate at this juncture. When I want this induction machine to work as a generator and feed back the power, all I need to do is to reduce the frequency from 50 Hertz to 48 Hertz or 45 Hertz or something like that. The moment I reduce the frequency, the revolving magnetic field speed will automatically come down. So I'm going to have whatever is the revolving magnetic field speed under this condition, that is going to become less than omega r, which happens to be 1450 RPM. This is during braking. Whereas for motoring, I am going to have the slip to be positive, and I'm going to have 1500 RPM as the synchronous speed. And that will be definitely greater than whatever is the rotor speed at that time when it is motoring operation. Now, after all, VSI normally has the devices somewhat like this. It is going to be a diode in parallel with IGBT or MOSFET. So these diodes can take over the rectification process of the three-phase voltage that comes out, and that can feed back to the battery through the DC to DC converter, provided this is a bidirectional converter. So unless it is a bidirectional converter, it would not be able to work properly. So in all the electric vehicles, especially regenerative braking becomes extremely important, because charging the battery can increase the range of the vehicle, and you need not waste the kinetic energy stored in the rotating parts also. So when you want to implement regenerative braking, generally the DC to DC converter will be a bidirectional converter, and the inverter devices will be able to automatically do the process of rectifying the voltage that is coming out of the three-phase induction machine, which is now working as a generator. So braking, especially in the form of regenerative braking, can be implemented properly provided we have a voltage source inverter in place. So in the next class, we would be looking at the functioning of a three-phase induction motor with an inverter. We call that as initially scalar control. We will be looking at initially scalar control or voltage and frequency control or V by F control. So we will be looking at this in the next class.